There's a number that mathematicians struggled to accept for years. A number that represented an idea so bizarre that it challenged the entire structure of the then accepted mathematics. And for years, mathematicians tried to avoid it. But eventually, they had to deal with it, and when they did, math was changed forever. The number line is a system that places each number at a specific position relative to zero. All real numbers, integers, fractions, even irrational numbers, can be placed on a number line, where the sign indicates direction. But how do you plot the square root of a negative number? Normally, the negative sign simply represents a direction. But the square root of a negative? What does that mean? That's not positive or negative. I represents the imaginary number, or the number whose square is -1. This may seem like common knowledge to you, but the idea of I was an obstacle that mathematicians struggled with for centuries. While the square root of negative numbers did confuse mathematicians, what bothered many mathematicians the most was negative numbers themselves. For a long time, as far back as the Greeks, math was understood geometrically. From a geometric point of view, logically, only positive numbers make sense. Lengths in geometry can only be positive. Negative numbers just don't work. How do you have a negative length or a negative area? Since negative numbers could not be understood geometrically, for years, mathematicians tried to avoid them altogether. But eventually, negative numbers simply could not be avoided. Mathematicians had been solving linear equations and quadratics for a long time, but for millennia, they couldn't figure out how to solve cubic equations. It wasn't until the 1500s that a mathematician named Niccolo Tartaglia was able to find the solution for a depressed cubic, or a cubic equation that doesn't have the quadratic term. Later, the formula for his solution was published by Girolamo Cardano in his work The Ars Magna. Today, we actually call this formula Cardano's formula. This equation is rather dense, and if you want to see how to derive this, check out the video linked in the top right corner. This solution worked fine for some cubic equations, but sometimes something strange would happen. Notice, for a depressed cubic like this, after substituting in for p and q, we get the square root of a negative number. Many mathematicians thought negative numbers were bad enough, but now the square root of a negative? Neither Tartaglia nor Cardano could explain this. Cardano thought there was no solution if the formula involved the square root of negative numbers, which he called fictitious. But notice, in this cubic, there is a real solution. 4. Then Rafael Bombelli came along, and he did something mathematicians hadn't dared to do before. What if the square root of a negative number was its own special number? Bombelli defined a number whose square was equivalent to -1. We call that I. Because of that, Bombelli was able to solve cubic equations that were once deemed insolvable. Interestingly, the imaginary parts canceled out and he was left with a real solution. We'll simplify this later in the video. Bombelli's discovery was astonishing, and the square root of -1 seemed like a loophole. Recognizing the square root of -1 as a number wasn't a revolutionary discovery that instantly radicalized math. There was quite a bit of resistance, and growth progressed slowly. Even after Bombelli's achievement, many mathematicians were skeptical. A renowned mathematician named René Descartes thought this number was useless, calling it imaginary, and the name stuck. Despite resistance, eventually the imaginary number became widely accepted and evolved into the number I we know today. But even today, I still stirs confusion among people. I represents the number whose square is -1. It also represents the principal root of -1. Taking the principal root of negatives requires some algebraic ideas to be handled more carefully because it's not a real number. For example, to find the principal root of 1600, you could separate 1600 into the product of two numbers, 16 and 100, and then take the square roots separately. The end product is 4 times 10, or 40, which is indeed the principal root of 1600. Great, no problem, that's the correct solution. But you have to be careful. You can't separate 1600 into the product of -16 and -100. These negative square roots give 4i times 10i, which makes -40. And while this is a square root of 1600, it's not the principal root of 1600. The principal root has to be positive since the square root is a function. Imaginary numbers require caution because they aren't considered real numbers. They are different. And this difference leads to one of the most powerful properties of I. As mentioned in the beginning of the video, we can't plot I normally on a Cartesian plane or a number line, but we can modify the plane and make a complex plane. Now, I is comprehensively visual. It simply means up or down on a coordinate system. Since I squared represents -1, as you take higher powers of I, you go through a cycle. I, -1, -I, and 1. This behavior should remind you of something very similar on a Cartesian plane. Every time you multiply by I, you're rotating by 90 degrees. This idea leads to a really cool and powerful connection. On a complex plane, I behaves very similarly to the unit circle on the Cartesian plane. Here, cosine represents the real portion, while sine deals with the imaginary or the vertical portion. This rectangular form can be rewritten in polar form, which is abbreviated with CIS. Now, recall the equation that we were trying to solve earlier. Using polar form, we can visualize what Bombelli discovered. Let's graph the two complex numbers from our reduced formula earlier. Notice that these are in rectangular form, so let's rewrite them in polar form. We can find the hypotenuse using the Pythagorean theorem, and we can find the angles using the inverse tangent. So now we have the polar form, which we can simplify. And for the 2 minus 11i, it's the same idea except the angle is negative. Now, we can take the cube roots of the points. And once we have that, we're going to turn it back to rectangular form and simplify. And once we add them together, the sum is 4. Understanding I cleared the path to solve cubics that were once deemed unsolvable. The number is so radical that it has its own coordinate system, the complex plane. What started as a confusing square root of a negative number led mathematicians through centuries of debate. From the rejection of negative numbers, to Tartaglia's cubic formula, to Bombelli's bold idea that this strange quality should be treated like a number at all. And in doing so, math expanded beyond the number line into an entirely new dimension. If you found the number I interesting, subscribe, because there's another number that mathematicians have been studying for thousands of years, and we still don't fully understand it.